do this a few minutes introduction and then we'll get started. Is that okay? Okay. So since we're already live on YouTube, so let me just get started. Welcome to the ARL seminar today. It's our great honor to have Professor Mengdi Wang from the Department of Electrical Engineering and the Center for Statistics and Machine Learning at Princeton University. She's also affiliated with the Department of Computer Science and a visitor research scientist at DeepMind. Her research focuses on data-driven stochastic optimization and applications in machine and reinforcement learning. She received her PhD in electrical engineering and computer science from MIT in 2013. At MIT, Mengdi was affiliated with the Lab for Information and Decision Systems and was advised by Dmitry Bersakas. Mengdi received the Young Researcher Prize in Continuous Optimization of the Mathematical Optimization Society in 2016, the Princeton SEAS Innovation Awards in 2016, the NSF Career Award in 2017, the Google Faculty Award in 2017, and the MIT Tech Review 35 Under 35 Innovation Award in 2018. She serves as Associate Editor for Operation Research and Mathematics of Operations Research, as Area Chair for ICML, NeurIPS, AI Stats, and is on the editorial board of a Journal of Machine Learning Research. Her research is supported by NSF, AFOSR, NIH, ONR, Google, Microsoft, C3.ai, DTI, FinUp. So without further ado, let's welcome Mengdi. Mengdi, you can get started. Hi, Mengdi, you're muted.
Hello, is my screen working?
Yeah, your screen is working and we can hear you now. Great.
Oh, okay, perfect. I'm trying to, close all the windows. Okay, good morning. Thank you very much for the invitation. So I'm going to talk about representation learning in reinforcement learning, and actually motivated by reinforcement learning, but beyond reinforcement learning. Okay, so this is joint work with, well, I'll show you my collaborators in the last slide. Okay, so let's get into the subject. So you can see, like, we want to do state representation learning, because that's going to be my keyword. And the motivation for state representation learning is we want to eventually be able to handle reinforcement learning applications and or data science applications when we don't have a lot of data and when we don't have the power to do a massive amount of experiments. Okay, so let's revisit the theoretical motivation for representation learning. So in RL, suppose that we don't have any structure and we don't have any prior knowledge. In this case, we view every single state as entirely different from other states. Such problems are usually referred to as tabular MDP, tabular Markov decision process. Okay, so suppose that I have S states and A actions to choose from per state. Okay, and now if we want to learn the optimal policy for such a tabular Markov decision process with S states and A actions, the sample complexity is going to be proportional to number of states S times number of actions A. Okay, so this S and A with other parameters. So this is non-improvable. And so there are papers proving lower bounds showing that in order to find a near optimal policy with high fidelity, any algorithm needs sample size linear to S times A. So this is an information threshold lower bound. Okay, so in recent years, there are a couple of papers, including ours. So we were able to come up with algorithms that can actually process samples in the most efficient way, so that we can actually achieve epsilon optimal policy with high probability using a sample size that is nearly matching the lower bound up to polylog factors. Okay, so we don't really have to think about optimization and the information threshold limit. I think the key thing here is that I want to show that in the sharp lower bound and in the sharp upper bound, the sample size is proportional to S times A. So that's the cost we have to pay in terms of sample complexity when we work with tabular MDP, when we don't have good representations. Okay, so although we have sharp upper and lower bounds, but we are not happy about those results at all, because S, the state space that we work with, is way too big. Okay, so if we think about any computer game, the total number of raw states is usually some number like 2 to the power of 100 or even bigger. So that's a typical number of S. And in continuous control problem, S is an infinite continuous set to begin with. We cannot even measure the cardinality of such an S. Okay, so apparently a tabular MDP or discrete state and actions are insufficient because we have too many unknowns about tabular MDP, and we hope to have something additional to help us to learn faster. So in reinforcement learning, either conventional approximate dynamic programming or more recently deep reinforcement learning, we always want to represent the raw state into a feature vector. Okay, suppose that we have such a state representation mapping per se. Then we can represent all different discrete states into a lower Euclidean space. Okay, so actually, this idea was first, not really first, but it was illustrated very nicely in the very first paper on deep Q network, in which we can visualize the neural network embedding of state of the Atari game, and we can visualize the distribution of the full state space in the lower dimensional embedding space, and we can compare which states are closer to other states. So if we have such a good such a good state embedding map, then we can do a lot of things. So first, we can use latent state vectors to identify latent structures and have better interpretability. So if psi is of lower dimension, then we can do functional approximation to reduce both sample complexity and also to improve generalizability based on batch data. Okay, we can also accelerate exploration, so we can learn faster and explore the unknown environment faster if we have a good embedding state representation map. Okay, so one rigorous theoretical motivation is as follows. So if we use a linear combination of state features to approximate the value of a state, okay, and also if we use a linear factor model to represent the unknown transition operator pi, we don't have to know the true value function and we don't have to know p pi. We only need to assume that the unknown value and unknown linear transition operator live in our feature space. So under this assumption, the minimax optimal sample complexity for solving the Markov decision process is going to be substantially reduced when we have such a good feature map. So we used to have dependence on S times A. But if we do have good feature maps, S and A will reduce to the dimension of the state feature map and the dimension of the action feature map. Okay, so if we can find psi satisfying this relation and also this relation, then this knowledge of psi is already going to save us a lot in terms of computation and sample overhead when solving reinforcement learning. And secondly, when we have good state representations, and if I'm using phi here. I'm using phi and psi interchangeably in my talk. So if we have a good state action feature map, so that this feature map is sufficient to do state-to-state prediction using a linear model, under this assumption, then we can actually make Q updates by combining fitted Q iteration with exploration bonus. And then the regret of reinforcement learning using this particular feature map is going to no longer depend on S times A, but depends on dimension D of the feature map. It can be linearly or close to linearly depending on the particular theoretical assumptions that we make. Okay, so now look at the two theoretical motivations tell us that we hope to have psi such that psi can embed the unknown functions and unknown transition operator using a linear model. And once we have such a psi, we can reduce sample complexity and regret by a huge amount. Okay. So in my talk today, I'm going to focus on how to learn such a good state embedding map psi. Okay, so recall that what we want to do is that we want to summarize information in the raw observation into a vector psi of S. So this map should be preserving information about the raw state. But hopefully this psi is simpler than the raw observation. Okay, so I searched for the definition of state variable on Wikipedia. So when we have a dynamical system, we can model states in different ways, right? But a good state variable is usually going to be a collection of variables so that we can describe mathematically the state of the system. So the state should be enough to lead on to future states. So it has to describe enough about the system to determine its future behavior, right? So that will be a good state of the system. And also we want our state to be a minimal statistics in a way that I don't want to have a bunch of junk information in my state. I want my state to be as low dimensional as possible in order to make downstream machine learning and downstream reinforcement learning more generalizable. Okay, so to put this definition of state variables mathematically, so I'm going to say that I want my psi to have such a property. So when we apply our psi map to two different raw states, S and S prime, okay, so the low dimensional vector after applying psi, okay, so we're going to say that if psi of S is similar to psi of S prime, this should only happen when the two raw states, S and S prime, they have similar future dynamics. And I'm going to measure this by looking at the difference between the conditional transition density, condition on the two different raw states respectively. Okay, so in other words, so basically what we really want is that my psi of S should be a compression of the full transition density from S. So we're not really compressing state. We're trying to compress the conditional transition distribution of a state into a vector. So that's our goal. Okay. So we have talked about a number of motivations. Okay. So let's make a summary. So we want to make sure that our psi is going to be giving me a feature space, and hopefully this feature space should be enough to cover all the value functions that we care about. Okay. And the related objective is I want to be able to use psi to evaluate functions of the form PV. So whenever we apply the transition operator of our reinforcement learning system to a value function, okay, I want this outcome, the function PV, also lives in the feature space given by psi. Okay. And further, I want to make sure that psi preserves some very important notion of distance. So we're going to measure the distance between two states S and S prime by some particular divergence between their respective transition density function. So we want this particular distance to be preserved after we map raw states into the feature space. And finally, we hope our psi to have small dimensions. Okay. So actually, there's a very simple answer. There's a very simple solution to psi that satisfies all these conditions that we like. So it's easy to see that the best psi should come from functional factorization of the transition operator of the Markov process. So if the transition operator happens to be low rank, then it means that we can preserve dynamics exactly into a lower dimensional space. Okay, and if the transition operator is approximately low rank, as in many physical systems, then we can approximate the high dimensional transition operator by projecting it onto a lower dimensional space. Okay, so we first analyzed how to learn how to learn the best psi by factorizing a discrete Markov model. And we were able to prove sharp upper bounds and information theoretical lower bounds. And this paper was a paper 2 years ago appearing at the IEEE Journal on Information Theory. So to really make this work, we are not happy with discrete systems. So let's consider a real problem in which we work with state trajectories where each state is a multivariate, has multiple dimensions or even high dimensions. Okay, so we can think about this sequence of X. It can be, for example, a sequence of images from a Atari game or from even a more complicated game. Or this sequence can be the clinical, can be the time series coming from clinical records of a patient. So this sequence can also be the single cell gene expression time series from biological labs. Okay, but in all of these applications, we want to handle multivariate time series. Okay, and our goal is to approximately estimate the spectral decomposition of the transition operator of the time series. Okay, and hopefully we can find a state embedding map, this psi, such that the span of the psi function is close to the span of the left principal component functions U here of the unknown transition operator P. So that's our objective. Okay, so we actually we provided a kernelized state embedding algorithm for doing so. So the high-level idea is that we start with our time series data, our state transition trajectories. And what we want to do is we want to lift the dimension of my data to an even higher dimensional space, so we can flatten out the dynamics and estimate a projection of the underlying transition operator onto the lifted dimensional space. And finally, we want to apply some variant of low-rank compression to compress the projected transition operator we estimated by lifting dimension. And eventually, we are going to put together all the steps that we have computed so far to eventually output a low-dimensional state vector for every possible original route state. Okay, so I'm going to skip the mathematical detail, but it's really trying to fit a low-rank state mapping to achieve the objectives that I just described. Okay, and we can indeed prove some strong theory. So we can show that if we measure the distance between two route states using a kernelized diffusion distance, which is defined by some particular kernel norm of the difference between the transition density from X and the transition density from Y. So this is known as a kernelized diffusion distance. So such diffusion distance is actually very commonly used in molecular dynamics in order to measure and describe the dynamics of a complicated high-dimensional transition system. But now we are borrowing this concept to our reinforcement learning setting. So we want to learn state embeddings to largely preserve this diffusion distance. Okay, so we can actually show that our estimated embedding map per psi hat is going to largely preserve the divergence in the high dimensional space of distributions. We can preserve that complicated diffusion distance in our lower dimensional compressed state space. And we can provide upper bounds and show that it holds with probability close to 1. Okay, so the theoretical upper bound basically tells us that we don't need our data sets, here little n, to be too big. The data sets little n should be bigger than the intrinsic underlying dimension of the system, but n doesn't have to be as big as the raw dimension of the system. Okay, so that's the theoretical result. And further, we can utilize our learned embedding to cluster states. So our goal is to make sure that we can find a partition omega 1 to omega m of the raw state space such that within each block, the transition density from a single state should be close to some central transition function representing the entire block. So that's a very natural loss function to aggregate states into blocks. Okay, and it turns out that this particular optimization problem is equivalent to finding the optimal metastable partition of the system. So metastability is again a notion from control and dynamical systems to measure whether a particular region of the state space is stable across time. So if we can cluster states according to similarity in their future dynamics, this is equivalent to finding clusters that are metastable across time. Okay, and we can indeed do so because we have estimated low dimensional state vectors to preserve this diffusion distance. So we can simply do clustering in our estimated lower dimensional embedding state in embedding space. So we can always learn from random walk trajectories or even high dimensional random walks. We can learn from psi hat and use our embedding map psi hat to find metastable clusters of the system. Okay, so that's the theory. So I'm going to illustrate a number of examples. So the first example is a very simple simulation. So we simulated a diffusion process from a potential function. So we can think about this diffusion process is really pretty much like doing stochastic gradient descent using this potential function as the objective. Okay. And then we simulate the diffusion process for really only very few samples. And then we applied our learned embedding methods to identify metastable clusters. So we can apparently see that by tuning the level of resolution, we can identify regions of the raw state space with different level of similarity and different level of stability. And we can quantify dynamics that are very fast and dynamics that are very slow. Okay, and this is expected because we designed the algorithm to do so. Okay, another example is for an Atari game. So this is a game known as Diamond Attack. It is one of the first games. Okay, so basically what we are the player, right? So we can control this pink cannon. So we can move it around on the horizontal line. And the diamonds, which are like this bird-like things, they are going to show up and fly around randomly, and they're trying to shoot the player. And the cannon can also shoot the diamonds. Okay. So we apply our methods to diamond attack. And we pick a particular kernel. We pick our kernel space to be the composition between the neural tangent kernel and the Gaussian kernel. So basically, we're first using one neural network to learn an initial embedding. And then we use random forward features to lift the neural network embedding to even higher dimensions with a lot of randomness. And finally, we apply low-rank compression. So this entire pipeline is going to map one raw state. Here, the raw state X is a raw pixel image of the game. But we can map this raw state into psi of X, which is a vector of dimension 6 or 7. Okay. So we trained our embedding map to figure out the best psi. So we use t-SNE to visualize the distribution of raw states and the distribution of embedded states after we apply the compression state representation map. Okay, so if you're familiar with t-SNE, you can actually easy to see that the left one, the raw states before embedding. So there's actually not much structure there, but after embedding, we have higher granularity and more clear clusters. And so I try to understand, so the map before embedding to after embedding, apparently this map is reducing the distance, right? We're mapping high dimensional data to a lower dimensional space. So some distance gets reduced or compressed after embedding. So we try to identify pairs of states that are close after embedding. So they are close in the lower dimensional learned state space, but they are far away in their original image space. So we identify several pairs to do a case-by-case analysis. Okay, so it's interesting because I actually could see that in those pairs, the two images share very similar strategic meanings, but they are different states. Okay. For example, let's look at the two circles here. So those are two images. And we as humans, we can easily see that this state is similar to the state on the right because the cannon is in a similar position. And in both images, the cannon just shot to this purple dash, and the purple dash is about to reach the cannon. Sorry, that is to reach the target. So this is a state where the cannon is in a similar position and the cannon is about to score. So we can easily see that those two images look differently. But if you look at the two circles are actually far away before we apply our embedding approach, meaning that the neural network, which embeds the first state here and the second state here, the neural network actually considers those two images as not very similar. Okay. Let's look at the last pair. So this pair, we can see that in both images, nothing is really happening. So our cannon is pretty much idling and there are no targets flying above. But what's interesting is if we look at the relative position between the purple dash and the cannon, we see that this cannon here is moving from left to center. And the other cannon on the other plot is moving from right to center. So they're actually at different locations, but they are moving to similar states, which means that if we are the player and we make decisions, we should expect to make similar distributions in the future dynamics from those two states. Okay, so we can see that the two states are similar in terms of when we actually play the game. But again, those two data points are actually far away before our low rank embedding, but they are on top of each other after we applied our state embedding approach. Okay, so that's a second example. So thirdly, I just want to mention that I was mainly talking about learning state representations by low rank approximation, but we can actually learn low dimensional disentangled state representation and action representations separately for Markov decision process. So the difference is that we're going to use a low rank tensor approximation approach. So even if we start with continuous state action transition kernel, we can use kernelization and random features to kernelize and estimate an embedded transition operator. And then we can apply Tucker decomposition to factor our learned embedding tensor along the state direction and action direction separately. And eventually, we can identify state embedding map and action embedding map to approximately capture the dynamics of the Markov decision process. Okay. So we applied this approach in a clinical problem. So this problem was motivated. So this problem is about clinical decisions for a particular treatment, which is known as the knee replacement treatment. So knee replacement, actually knee and hip replacements. So together, they are actually the most popular surgical treatments people do in the US. And about 700,000 procedures take place every year. Okay. So what happens is this usually happens to seniors. So a senior person, when his or her knees have issues, they will just go to the hospital and ask to have their knees replaced by metal ones. And my senior colleague in the department told me that, so one of the colleagues, he got his knee replaced and then he could ski again and he was super excited about his new knees. So this treatment is very common and it involves multiple decisions and a horizon up to 100 days or even longer horizon. So the cost of the entire treatment episode is pretty variable. So it depends on whether this patient gets well soon, or sometimes the patient can get complication and he has to go to rehab and he has to maybe come back for another surgeries. And the total number of decisions per episode, again, depend on whether this patient got lucky or this patient happens to enter into a tricky situation. Okay, so a few years ago, so the Medicare of US decided that they can no longer afford covering the cost for knee replacement for all the patients. So Medicare asked hospitals, say that, hey, so you guys cannot do whatever you want because the Medicare, the government cannot pay all the bills. So the hospitals are required to keep the cost per episode below a certain level. And if a hospital incurs a cost when treating a particular patient above this level, the hospital is going to be taken part of the cost premiums. Okay, so it was this change finally motivated the doctors and hospitals to say, hey, can we take a closer look into the clinical decision-making process and can we optimize it so that patients can get well sooner with fewer cost? Okay, so that's the background. So, so we use a clinical data set provided by a major healthcare insurance providers. So we have clinical records from 37 physicians, and we have data from more than 200 episodes with a large number of claims per episode. Okay, so the data is really a time series data. So we have an event whenever the patient receives a diagnosis or whenever the patient is prescribed certain medications. So we have a sequence of events with time steps. So the problem is the data set is actually not too big in the eyes of people who work on machine learning. But such a data set is actually considered very big for researchers in the medical domain, because in the medical domain, it's actually very hard to come up with a data set for a group of patients with similar age, similar background, similar context. Okay, so whenever we specialize to a particular group, having 200 episodes is usually considered as a big data set. Okay, so we want to learn the optimal treatment policy from this data set. Okay, so we can imagine that this is a data set in which we have state action, state transitions generated from behavioral policies. And the behavioral policies are the policies used by the actual care providers. Okay, so our idea is very simple. So there are too many different claims and too many different diagnosis codes. So we want to decompose the raw state space to appropriate resolution, right? And we're going to imitate behaviors of the physicians and try to do some optimization on top of what they have already done. Okay, so what we do is that we model the decision-making process for treating knee replacement as a Markov decision process. But the state, we cannot use the original discrete state. We apply our kernelized state embedding, where we choose kernels using existing graph knowledge about medical diagnosis, which is known in the literature. So we can choose an appropriate kernel. So we use kernel state embedding plus batch policy optimization to this particular data set in order to learn state embeddings together with a coarse-grained optimal policy. Okay, so I'll just show you the result. So we were able to learn the optimal policy from batch data, and we will actually also be able to do cross-validation and out-of-sample test. So our best result was actually we were able to reduce, let's see, what's the result? Okay, so we were able to reduce the per episode cost by $1,000 per episode. And that's an out-of-sample estimate of the improvement in value. So if we multiply this improvement by the total number of cases each year across US, so this small improvement we achieved using batch RL is already 700 million USD per year. Okay, and recall that we're not even using a big data set. We're not doing anything super fancy yet. We simply apply low rank state embedding together with batch policy optimization, and we already immediately see a credible improvement, which is an out of sample improvement. We can also use the data to predict the distribution of diagnosis and conditions of patients under the optimal policy. So we can predict the full distribution of states across time. So this will be helpful because we not only want to predict policy, we also want to predict that if we have a policy, what happens to the patient when we apply the policy. Okay, so that's a third example. So lastly, I want to talk about an example in biology. Okay. So you might have seen that we're actually making the problems harder and harder. So let's see. So the first example was a simulated diffusion system. And then we apply our method to Atari games. Atari games are hard, but because they are fundamentally games, because then we can run the games and generate tons of data. So games are hard, high-dimensional, and nonlinear, but we have a lot of data to learn embeddings. Okay. And then we have clinical records. We have, again, high dimensionality, discrete state space, but we have fewer data. And finally, the hardest example I'm going to present are single cell time series. I call them hardest because single cell time series are known for extremely high noise and a lack of patterns. Okay, and also for small data size as well. Okay, so what's interesting here is that recent technology in recent biotechnology enable us to track the state evolution of a cell very nicely. So by state evolutionist, I mean that we can use sequencing to measure the gene expression level in a single cell. So each gene has an activation level at a time point, and then we can measure this activation levels across genes for a single cell. So this is known as the gene expression profile of a cell, which is our raw state observation. Okay, so recent technology allow us to actually add a DNA sequence, which is a barcode to individual cell. So this is helpful because as cell grows, we can read the barcode to identify, hey, this is the cell from 2 days ago, or this is the descendant of a cell that I recognize. So we can recognize lineages between individual cells. Okay, so this is such data is typical with games, with clinical data, with dynamical systems, but such data is really new for single cell data, for single cell analysis. So now we basically have, I would say, time series for every individual single cell. So we can model the state transition of a cell using our tools and ideas from reinforcement learning. Okay. And also I need to mention that cells are very different from typical time series because cells can divide and branch. Okay, so in our data, we can actually recover such lineage tree with measured gene expression at every single cell or every single node in the lineage tree. Okay, so now we want to analyze such data, and hopefully we want to learn meaningful state representations for cells. Okay, so again, so we applied the approach I just described, but we did a lot of engineering and optimization to account for specific structures of single cell data. So what we can do is we can take as input single cell transition gene expression data. And finally, we can output a low dimensional state vector for every single cell in my data set. Okay, so the high level idea is still to do kernel dimension lifting, dimension reduction, and low rank compression. Okay, so we analyzed a stem cell reprogramming data set. So this is a data set in which we started with, not we, so scientists, they started with a collection of stem cells in their elementary state. And as time goes by, the stem cells sort of differentiate and they reprogram into different destinations. Okay, so we analyze the data. And so in this figure here, we are visualizing the cell-to-cell transition that we recovered from the cell barcodes. So what we can see here, so again, this is a t-SNE plot. So the real data is of dimension up to 5,000, but we're using t-SNE to visualize the data in 2 dimensions. So in this visualization, we can see that the state transition of cells are very discontinuous. There are big jumps. So because we are actually measuring the transition of a cell on day 12 and then day 21. So we have 9 days apart from a parent cell and a descendant cells. Okay, so we analyze such data. So we were able to map cell states into 3 dimensions. And what's very interesting is, so this is a visualization of our learned cell states in 3 dimensions. And we observe a very clear polytope structures with vertices. Okay, so I'm going to explain what they mean later. So after compressing cell states into very few dimensions, so we can use the learned cell state to do clustering. As I mentioned before, clustering of the low dimensional states is equivalent to finding the optimal metastable partition. So we can see that if we cluster cells on day 12 using our state, then those clusters remain concentrated after 9 days. But if we look at this cluster assignment in the raw data, so this is raw data before embedding, we see that all the colors are mixed together and on top of each other. So this means that the raw data has too many redundant dimensions so that the metastable structures are hidden in the original high dimensional data. But such structures are obvious after our embedding approach. Okay, so we can identify clusters of cells that are metastable. Okay, so what next? So we can also use our learned state variables to predict activities of cell descendants after 9 days. So we try to predict 2 different activities. They are known as cell cycle scores. So they are basically scores to measure the growth activities of cells after 9 days. And then we show that compared with approaches using the raw data, we can actually achieve similar level of accuracy using only a few dimensions as compared to other neural network approaches taking into raw principal components. So it means that we can actually be able to predict activities of cell descendants many days after using a few dimensions. So we are able to compress information by a lot. Okay, and more importantly, so when we try to analyze biological data set, we want to interpret what's happening. So we try to impose a latent state model, which means that the observed cell-to-cell transition, the observed random walk data may be driven by a simpler state transition system over a smaller set of metastates. So in this model, we believe that the raw gene expression profile of a cell hides information about the true underlying latent state. Okay, and under this model basically means that in the tabular case, the high dimensional transition matrix admits a non-negative decomposition. Okay, so that's the mathematical description of latent state model or soft state aggregation model for Markov process. So such structure also exists in single cell data. So what we do is we do our cell state learning as before. So suppose that this middle plane, so this is our three-dimensional state vectors of single cells. So what we do next is that we want to identify a polytope structure and we want to identify vertex of our cell states, because every single, I would say, every single cell in the middle is a convex combination of vertex. So this, we can translate it into probability. So in other words, this means that the dynamics from a middle state is a probabilistic mixture of dynamics from vertex states. So those vertex states are exactly the meta states that we're trying to identify in the latent variable model. Okay, so we did analysis. So in our data, we actually already observed that the top three dimensions of our learned cell states already demonstrate a super nice polytope. So we can identify cells that are close to the vertex, and then we run a differential analysis to identify marker genes and representative pathway of each vertex. So what's really exciting is, so I learned this from my collaborator. So what's really exciting that we clearly observe that the four vertices corresponds to different pathways of stem cell development. So vertex 1, for example, is this guy here, the bottom one. Vertex 1 is actually enriched for genes for developing brains and the neural system. Okay, and the vertex 0 is for liver and intestine. So this is really exciting. So apparently, so by using the state embedding approach, we don't have to know biology, but we can already easily identify vertex that corresponds to different pathways which match the known biology. And another interesting thing is, if you look at those yellow cells in the center, so they are actually representing a mixture between different tissue cells. And this again validates our model that states in the middle represents combinations or mixtures of extreme metastates. So finally, so why is this useful? So now we identified vertex, we identified metastates. So we can use such information to figure out top marker genes for each pathway. Okay, so the top marker genes, they are really known as pioneer factors. So they are going to be the genes that drive the development and differentiation of stem cells. So as long as we found those marker genes, we can use them as drug targets. So we can identify few meaningful targets by using this state embedding approach, and those targets can be potentially used as targets for developing molecular drugs. Okay, so that's the last example, and I want to thank my collaborators, including my collaborators across different universities and my students at Princeton University. Thank you very much.
Well, thank you, Mengdi, for the very interesting talk. We have a few questions. First question is from the Q&A board. Yan Xunxu asked, what's the exact possible treatments or clinical decisions for this knee replacement example? That's actually in the third example, right? I also have a lot of questions for that example. For example, what is the state, action, reward in that example? Could you help with this? Mengdi?
Yeah, the first one, so the clinical decisions are whatever decisions that are available in the data set. So I don't make up those clinical decisions. So the decision could be like which medicine to prescribe. And there are actually like up to 900 different medicines, but they are all possible clinical decisions.
So the action space is like about 900 dimension?
I think it's actually more than that. It's more than that.
And how about the state space?
I explained the state space is a history so far, but we use compression to map it to lower dimensions.
And so can I ask like how many, what's the number of stages, like how many horizons in that data?
Yeah, I explained the horizon, the actual horizon is up to 3 months, but the number of decisions is a variable. So some patients can just get discharged with 20 decisions. So some patients who end up with complications like 并发症, so they could stay in the hospital or come back to the hospital, and there will be a total of like up to 60 actions.
Yeah, that's
so
quite.
I would say it depends. Yeah. So it's not a discounted, it's not a finite horizon process. It's more like a total cost process with random stopping time.
I see. So then you define your value supposed to be just the total, maybe discounted cost. I'm just curious.
Oh, the value is given by our collaborator. So they have a metric which is a combination of cost and also the quality of care.
I see. So this is really not, can we say this is not that big compared with other examples? And
oh, the example is super big. The state space is actually a few thousands.
So for that example, also I have just a general question in terms of you're saying you're just trying to embed a project from a larger space to a low dimension space. So I'm curious, like, this is real data, so we don't have a ground truth. So in theory or in practice, how do you choose the dimension of the?
Yeah, we use cross validation, so our results are out of sample results.
I see.
Yeah, that's a great question. So that's a key step. If we don't do cross validation or bootstrapping, then it's very hard to choose the right level of model complexity.
Yeah, that's understandable. Thank you. Let's just move on to the next question. Can low dimensional representation be used to solve the adversarial attack issue? Adversarial attack issue?
No, I don't completely understand the question, but low dimensional representation is, I would say, is usually a prerequisite before we can do anything. But I don't think it is a method specific to solving the adversarial attack issues.
Yeah, for the anonymous attendee, if you want to be more clear, that may be helpful, but let's just move on to the next question. Sheng Zhang asked, this method embeds the state with the transition function. Can we do it similarly by embedding the state with the value function?
Well, if we use value, it's already one-dimensional. We don't have anything to embed, right? The transition function is high-dimensional. That's why we want to embed it. But if the value is already mapping the state to a scalar, so we don't have anything to embed here, right?
So it really depends. So if you do have a high-dimensional value, you probably can do that as well.
No, that's a different thing. We are using state embedding to reduce the dimensionality of value function, not the other way around. But actually, it's possible that if we have many value functions, we can use those value functions to learn state embedding that are specific to the task. So, but if we want to learn state embeddings for a dynamical system, not just a single reward or just a single value, then we have to work with the transition function.
I see. Yeah, that makes sense. So Is that possible to consider a possible extension? Like, can this type of embedding work for example, bandits problem, where you don't need to worry about state transition?
I think for bandit problem, that would be pretty trivial, right? In the bandit problem, we don't have dynamical system, so we can use any metric, not any, but that will reduce the problem to a more typical metric learning or dimension reduction problem in bandit.
Yeah, that's probably true, but I'm just curious. Still, for that medical example, the third example, I'm just curious. Like when you collaborate with your collaborator, how do people really model those those disease progression process? Because I think it's quite difficult for different particular medical studies. So I'm just curious, would that be a difficulty to just consider this different state transition?
I actually think it's not as hard as I expected.
Okay.
Yeah, because we do have initial kernels, and kernel can represent relational relationships, right? And so there are existing database with relational graphs. So those information can definitely be helpful.
Yeah, because I also work a lot with those medical record data, and one thing I commonly notice that MDP assumption is just not the case in practice. So that's why I'm just curious, because for your case, it seems like your number of episodes is, you're saying, for different patients is different, and that's why I'm just wondering, like if modeling state transition can be a difficulty, or also I'm just curious, in that case, if the dimension is not that high for the state.
No, I would say the state of the process is not that high, but our raw state is the history, is the collection of states.
Yes, the collection of the states. So can I ask, like, how high dimension that is if you collect all the history? What's the dimension for the collection of the history if you're so in that case you're
Yeah, but it's a variable, right? It's a time series. It's also a time series, and it's a variable.
True.
Yeah.
But I'm just curious if that's possible to compare the analysis of the original data, using the original data instead of doing this embedding, and compare with the result after embedding.
Oh no, we cannot compare. There's nothing to learn in the original data. So even if we don't worry about history, the number of states is bigger than the number of episodes we have.
Okay. Oh, we have another question. Tony asked the question, how does the low rank tensor decomposition affect the performance of the state embedding? In particular, Tucker decomposition requires the input of the rank. Is the determination of that rank important?
I think the determination of the rank, this is really Ray's previous question, right? Whenever we want to do model reduction, we want to pick the appropriate model complexity. So this is, I would think about this as a model selection problem. So in either the matrix or the matrix case or the tensor case, we all need to choose the rank. And theoretically, choosing the right rank would require knowledge about the eigengap. But practically, we want to do cross-validation and bootstrapping to choose the appropriate rank based on the data.
So are there any way, or I'm not sure if it's something of interest in your field, for example, to verify in this case, if the cross-validation can give you a reasonably good result? It's a data-oriented method, but do we care about, for example, if the cross-validation can really give us the one that's close to the ground truth? Is that something of interest?
Sorry, can you say it again?
Oh, I'm saying, do we have any theoretical validation for apply cross-validation here to choose the dimension or the determination of the rank?
Not to my knowledge. Maybe there's some paper on that. But we have papers on bootstrapping, which is very similar to cross-validation. So cross-validation or bootstrapping, I would say they are similar, but would definitely asymptotically give us the right model, and also we can use that to calculate, I would say, to approximate the distribution of our estimation error.
I see. So
that basically bootstrapping, so tools such as bootstrapping work for off-policy RL. So there's paper on that.
Okay. So Renjo Wang asked a question. First, I see the theory is based on the assumption that the low rank embedding is exact. Did you consider the approximation error? Mengdi, do you want to answer this first?
Yeah, with the approximation error will be depending on the eigenfunction of the transition operator.
So you did have the analysis, the approximation error in your results, you're saying, right?
Oh yeah, that one is pretty straightforward.
So second question, the current proposal seems fully offline. Do you think there would be some online applications and we can extend the method?
Oh, definitely. So learning stable representation in online RL is a very active subject, and also it's related to online model selection, and there are very interesting results on that problem. But I would say that online RL and the offline RL are completely different problems. So I wouldn't say that online RL is an extension of offline RL, because in the two problems, we actually care about very different things, and we can access very different information. So I think the idea would definitely work online, but that's another problem. It's not a follow-up of this problem.
So the third question, in the Atari example, if the embedding is to approximate the state transition, where S is the next screenshot, why two different screenshots will be close?
Yeah, good question. Very good question. Because we are using a Hilbert space norm. We're not comparing density with density. We are projecting the density to a kernel space, and we're comparing their projections.
So the next question, what does close future trajectories mean in this case?
It means that their future states have similar expectations. I mean, it's just closeness in the Hilbert space norm.
I see. So I have a question related with Ranger's first question. It seems like your method really has a big improvement in terms of the rate, for the error bound. You can really just decrease the dimension dramatically. Does that come without a price? So what price should we pay here? Do we have any loss? Do we have any, yeah, I guess then the question is what price do we have to pay here?
Representation learning is unsupervised learning. So representation learning and unsupervised learning in general is harder than supervised learning. So if I want to predict a single function, so this problem is harder than mapping the original data into lower dimensions. So I guess that's the price to pay. So the complexity is definitely higher than a simple supervised learning problem.
So, okay. We have another question on the Q&A window. Let's just move on to that one. The first is, I see the theory is based on the assumption that the low rank embedding is exact. I think Renjo, you copy paste here, right? So it's the same question. So we don't need to redo this again. Yue, do you have any other collections of the questions from other social media?
No, we don't have.
Okay, well, we're already run out of time. Well, thank you so much, Mengdi, for the very, very interesting and insightful talk. Any other comments so far? So yeah, I have a last question. So you do have a lot of applications. So I'm just curious, for that medical application, do you work on, for example, you did seem to have some successful reinforcement learning strategy, although I would have to say the last application, I did not really get the RL components there. I saw you were working on the gene selection. So was that a RL question? Did I miss the RL component?
No, that's not an RL question yet, but the reason that it is not an RL problem is because the raw state space is too high and data is too small. So if we can map states into lower dimensions, it will be possible to make it an RL problem.
So yeah, that makes sense, right? Because this embedding representation stuff definitely can exist without combining with RL technique. And but for the third application, did your collaborator, are you considering putting that into practice? It does seem to be able to save a lot of money.
Oh, we patented it. Yeah.
I see. So also for the, I think that's also maybe related with Rendra's last question. So or maybe not. So I remember you have a very nice plot where you just show the embedding seems to, yeah, that's really Rendra's last question. I'm just curious, are there any negative case, for example? So does your embedding always just capture the right information? Or I have to say this way, your method built on the assumption that there does exist a low dimensional intrinsic structure. How do I know in practice if there does exist low dimension? What if this intrinsic dimension is really high dimension? In that case, what can we do?
Oh, if our matrix or tensor is full rank, we cannot do low rank approximation. Then it means that the problem has rich structures. We cannot do compression. So that's a good question. But actually, I think the real hurdle here is not about whether there exists lower dimensional structures or not. Usually there usually, I would say 99% of chance there exists lower dimensional structures. But I think the real issue is whether there are confounding factors. But this is a problem not only to state representation problem. This is a problem to RL in general. Whenever we model the states, are our raw states sufficient to capture the entire information? I think that's a question that could be challenging. And if there are confounding factors that we don't know, then it's hard to say whether we can learn anything meaningful at lower dimensional or not from the batch data.
Are you talking about the confounding is like a causal confounding, something latent?
Yeah, something like that. For example, if there are something about the patient which we don't know or which is not recorded in the data, and that's a problem, right? That's why we actually need to specify the data set in a way that all the patients are similar, have similar demographics. But whether that's really true is not something we can handle.
Yeah, that's
so if there's some outlier with some particular situation we just don't know, but we are counting that patient, then it could make learning anything hard.
Yeah, because your current assumption is the observable states can characterize
yeah, because we are making an assumption that we are working with Markov decision process.
True. Yeah, there exists a recently growing literature about the causal reinforcement learning. People try to consider RL with a magic confounder and find some ways to adjust for those confounder. Probably in the later series, we can invite speakers to talk about that topic. That said, I think we can close our discussion today. Thank you so much.
Can I ask a question?
Oh, yes, please. Of course.
No, I think I think there was always a wonderful talk. I think I have a question regarding to your using kernel trick. And because we know that if the data dimension is really high dimensions, and the kernel trick is suffer from the curse of dimensionality, because you have how to choosing the tuning parameter in kernels, and when you're using L2 norm or other norms, basically that suffer from the curse of dimensionality. How do you deal with that?
Oh, we use random features. We don't really deal with the actual kernels.
Okay.
Does that answer your question?
No, yeah. You're using the random features.
We're using random features, and we also use neural networks. We actually use neural networks as part of the kernel. So by kernel, I'm really talking about higher level, I mean, just kernel as an informal concept. It doesn't have to be a particular Gaussian kernel.
Okay. That's your point. Thank you.
Thank you.
Okay, so I think we can conclude our session today. Well, thank you so much, Mengdi, and thank you everyone for being here. We'll see you next time.
Thank you.
Thank you.